Hello everyone. I'd like to go over breadth first search and depth first search in graphs. It's something we did in class, but I'd like to make sure that you have a reference video to go along with it because these are very important algorithms. So I'm going to start here by showing a little applet that I made for my AI class that demonstrates the ideas. So breadth first search and depth first search are examples of what are known as blind search algorithms in graphs. So what we're doing is starting at a particular vertex in a graph and exploring everything that we can reach by a path from that vertex. And so, for example, let's say that I'm in this graph in the 2D plane. Each vertex here is going to be depicted by a pixel, and I might be connected to adjacent pixels if they happen to be in this graph. And so you could think of this like a maze in 2 dimensions that I'm exploring. And I'm going to show here in white the vertices, or the pixels here that I've explored, and the ones in gray which are connected to vertices that I've explored but that I have not actually walked to yet. So in white are the ones that I visited, and gray are the ones that are on what are called the frontier. And so there's any number of ways that I could choose to expand the frontier or visit things on the frontier. Here I'm just kind of clicking around. And so every time I click on something on the frontier, I visit it, and then I add its neighbors that haven't been visited yet and are not on the frontier to the frontier. So here I have these 1, 2, 3, 4 points on the frontier. And I just keep expanding them. And, if I just continue expanding them, eventually I will reach everything that I could reach from a path from where I started around here. So eventually I will enumerate all of the vertices in the connected component that the original one that I started with is a member of. So just like when we started off with trees and we had pre-order, in-order, and post-order for exploring all the nodes in a tree, we're going to have breadth first search and depth first search as algorithms to explore all the vertices in a graph. So unlike a list where we knew we would just walk from left to right, in a graph we don't really exactly know where to go from where we start. So we need to spend a little bit more time thinking about how we might explore. So let's see what depth first search does. Or actually, let me show breadth first search first. So breadth first search will expand the frontier in increasing order of distance from where we started. So notice how it's going out evenly in all directions. It's almost as if I dropped a stone on a pond and the ripples were going out in a circular pattern. So that is breadth first search. Actually, here there's a little target that maybe I'm looking for a particular vertex in the graph. I draw it as a red dot here. So that goes out evenly in all directions. Depth first search, on the other hand, continually goes in one direction until it reaches a dead end. Actually, if I was looking for the prize here, I got kind of lucky. Let me go to another maze. So, actually, let's do Matt's maze, the little Pac-Man maze. So depth first search is going to go along one direction until it reaches a dead end, or something it's already visited before. Then it's going to back up and try something else. So see, it keeps going along one direction until it reaches a dead end. It's a little bit different from breadth first search, which goes evenly out in all directions on the frontier. So here it's leaving a lot of directions on the frontier open until it finishes exploring one, and then it comes back. Okay, let's discuss now how to do some of this in code in Python. So what I've done here is I've created a little graph off to the left that I'll represent here and use as an example. But let me go ahead and define something like an adjacency data structure for a graph, but this time I'm going to make a node a first class object, or a vertex a first class object. So what I'll do is I'll have an object where it just has a single instance variable for now called neighbors, which will store the neighbors of this vertex. And then maybe I'll have a graph class that organizes them or stores them together. And I'll say self.vertices. And you know what, I'll make this a dictionary, because what I'll do is I'll say, okay, the key is you know what you look up. So the key is the vertex to look up, and the value is the object encapsulating information about that vertex. Okay, so let me try to make the, oh, and actually, yeah, let me add a couple methods in the API here, because I'll say maybe, you know, add vertex is a method. And so I'll say, in this case, I'll say self.vertices u is equal to this new vertex object. And then I'll say, maybe I want to add an edge. In that case, I'll say self.vertices u.nabes.add v. And then I'll say self.vertices v. I want v's to have the neighbor u. So they're each other's neighbors, and that actually should be good in the data structure. So very similar to the adjacency data structure I created before, but I have one extra little thing here, which I've created a class for a vertex for itself. That's going to make it a little bit more convenient for me in a moment to do breadth first search and depth first search. So let me set up the graph that I have depicted here. The vertices could be anything that's hashable, you know, because I'm looking up the key in the dictionary. But for now, I'll just make them the 8 numbers from 0 to 7 inclusive. So I'll say for v in range 8. Actually, let me make my little graph object first. I'll say graph is equal to new graph, and I'll say graph.add vertex v here. That code ran okay, didn't complain about anything. So let me go ahead and add these edges. So I'll say graph.add edge 0, 1, graph.add edge 1, 4, and give me a second and I'll finish this up. Okay, so I added 8 edges here. As a sanity check, this is a graph with 8 vertices. I know that if it were actually a tree, so say I were to remove this edge, then it would be a tree, it doesn't have a cycle. I know in that case it would have 1 fewer edge than there are vertices, so 7 edges. But it just fails to be a tree. I add 1 extra edge there and create a cycle. So I go from 7 edges to 8 edges there. All right, now let's talk about how to do breadth first search and depth first search here. So what I want to do actually is keep track basically of whether a node is on the frontier, so those are the ones depicted in gray here, or if it's already been visited. So maybe what I'll do here is I'll make a little state of the vertex. And I'll have maybe 3 possible states. I'll say on frontier. So I'm going to define these as constants up here. Visited. And maybe one more state, which is untouched. And every vertex is going to start off as untouched. So these are just constants that I'll define up here to make the code a little bit more readable. And so let me make a little method here. So I'll say, maybe I'll call it explore. And this is what's going to run the algorithm. So I'll say, you know, run breadth first search or depth first search starting at the vertex u. That's what this method will do. Okay, so let me make a little legend here, because sometimes I like to think about this like a forest fire going along. So what I'll say, I have again those 3 states. One of them is untouched. So that, let me just put the text there. So that's untouched. And then I have on the frontier. In this case, I'll think about it's maybe like some kind of forest fire that is spreading. So I'll say here, this means to be on the frontier. That's what it means. I'll draw it as red as I'm going through this here. And then we have visited, which I'll think, you know, if it's a forest fire spreading, that's kind of like this thing has burned to the ground. So that's visited. So when we start, let's say that we were going to start the search at vertex 1 here. So what I'll do is I will make a data structure that keeps track of what's on the frontier. And I will start off the frontier as having u on it. Okay, so I'm going to put u starting off on fire. And I'll say, okay, as long as there's something still left on the frontier, then I still have work to do. So basically, I'm going to think about this like a forest fire that eventually burns down everything that's connected to where I start. So as long as there are still things on fire, the forest fire is still raging. I still have work to do. So what I'll do is I'll start by taking what's on the end of this off. So maybe, let me call this start. Just so it's very clear where I'm starting. Oops. And okay, here's what I'll do. I'll say this vertex V is what comes off of the end of the frontier. So remove from end. And now what I'm going to do is look at all the neighbors. Oh, actually, first, before I do that, if V comes off of the frontier, then it's burned to the ground. So if I started at 1, then that would turn to a black vertex. So let me make sure to say V dot state equals visited. Okay. So now what I'm going to do is look at each neighbor of V, because V is going to burn to the ground, but as it's burning to the ground, it's going to pass the fire along to its neighbors. So I'll say for n in V dot neighbors. So if that neighbor is not already on the frontier, and the neighbor has not burned to the ground yet, so if the neighbor is not on the frontier and it hasn't been visited yet, let me move this over just a little bit, then I want to add it to the frontier. So I'll switch to being on frontier and add to the back of the frontier. So I will say n.state then is equal to frontier. And I'll say frontier dot append n. Okay. So I should say here, while length of frontier is greater than 0. Okay, now the other thing I'll do here is just for now, I will print out the vertices every time they come off the frontier. And so we'll see what order that we visit them in. Okay, so that's the algorithm. So you know, I put a neighbor on the frontier if it hasn't been visited yet. So let's see what this does. First of all, I want to make sure, okay, the code ran. Let's see what this does when I explore starting at vertex 1. So if I were to say graph.explore starting at vertex 1. Well, I get an error that says int object has no state. Of course, what I meant to do was to go through this data structure here. I want to pull out the object associated to that. So I should have said here, frontier is equal to self.vertices start. And then I think I'm okay. And so I better then I'll make a, when I instantiate these or I add these, maybe I'll also keep track of a label. And I'll make a repr method. So if I go to print this object, it'll just print whatever the label is. So let me just test that real quick before I explore. So if I were to say print, I'll say maybe vertex 5 or something. So that prints out a 5. Okay, good. I think we're good now. So let me go back and see what happens when we try to explore from 1. Oh, still get a problem. Int object does not have attribute state. So it printed out the 1. That was where I started. And it was supposed to be the object there. So let's see. Let me also print out the type of this real quick. Yep, that's a vertex type. So supposedly, oh, I guess I should have said, one more place. When I go to add the neighbors, let me add the neighbors as the objects of the neighbor. Okay. So here the key in the dictionary is what I'm calling the vertex, but the value is what actually stores the objects. So I should have said self.vertices v in here, self.vertices view. Okay, I think my data structure is finally in order. I know I said that last time, but let's see what happens now. Frontier is not defined. Oh, I said on frontier. Let me just call it frontier. Okay. And oh yeah, let me throw that print statement back in now. So when the thing comes off the frontier, let me print it out. Okay, finally, we have an enumeration of all the vertices. So let's see. First of all, we should have gone through everything. So we have 1, 3, 7, 4, 0, 2, 5, 6. So great, we visited everything. But why do we go in that particular order? So what I'll do here maybe is when this comes off of the frontier, let me print what's on the frontier, what's left. And we can take a look at it. So first, 1 is on the frontier. I take 1 off, there's nothing left. Actually, maybe it'll be better if I printed the frontier after I go through all the neighbors. So let me print that down here. Okay, let's look at this. All right, so first 1 comes off the frontier, 1 sets on, it burns to the ground. Then it sets its neighbors to be on the frontier. So that would be 0, 2, 3, and 4. So those now go on the frontier. And really in no particular order. The neighbors can come out in any order. The neighbors are in a set. So they go on there, 0, 4, 2, 3. Now when I go to remove from the end, the thing that happens to be on the end here is 3. So 3 is what's going to come off of the frontier next. And so I look at 3 and I say, okay, 3, it has 3 neighbors, 4, 1, and 7. Actually, 1 has already been visited and 4 is already on the frontier, so the only one that I add to the frontier is 7. So I'll burn this one to the ground, and then 7 gets added to the frontier. So I see after 3 has been finished, being processed, 7 gets on the frontier. So 7 was actually the last thing to come off the frontier, so 7 is actually the first thing to come out of the frontier. And so when 7 comes out, actually none of its neighbors are untouched, so nothing happens to the frontier. Then we take 2 out of the frontier, so we burn 7 down to the ground. 7 has now been visited. 2 is what's at the end of the frontier. We take that off, and it has 2 neighbors, one of which has already been visited, so we just burn 2 to the ground and add its neighbor 5 to the frontier. Now 5 is the last thing that was on the frontier, so I burn 5 to the ground and add its 1 neighbor, which hasn't been touched yet, to the frontier. And so the fire kind of spreads in this direction. And then 6 comes off, but it has no neighbors that haven't been touched. And so then finally we come back to 4, and then back to 0. So I want you to pause for a second and tell me, is this breadth first search, the one that goes out equally in all directions? Or is this depth first search, the one that completely finishes exploring one path until it gets to a dead end and comes back? So pause it for a second. And what you should be concluding here is that this is depth first search. Because if I back up and look at this again, so it goes out first starting at all the neighbors of 1, but then it finishes exploring in this direction, runs into a dead end. Then it explores in this direction all the way, runs into a dead end. Then it backs up and finally finishes up over here. So this is depth first search. And when we look at this, we're using really, the visited data structure is a stack in this case. So we're removing from the end. And so when we remove from the end, the last thing that we put on the end, that's a stack. So last in, first out. So let me pass along a parameter here. I'll say, so if it's breadth first search, I want to remove from the end. Sorry, if it's depth first search, I want to remove from the end. So depth first search uses the frontier like a stack. And then breadth first search is going to use the frontier like a queue. So here we say last in, first out. And here we're going to say first in, first out. So here I was using a list to represent the frontier. And that's perfectly okay when we're treating it like a stack, because we can append and remove from the end of the list very efficiently. Because the list is an array list, and behind the scenes we know that we can remove and add to the end efficiently. But if we want to change this to work like a queue, and we want to also be able to remove from the front efficiently, we should use a different data structure, because if we're using a de facto list in Python, removing from the front is not efficient. When you remove from the front, you have to shift everything over. So what I did here was I took some code that we had written a long time ago for doubly linked lists, which that's a data structure where we can remove from the beginning and the end, and add from the beginning and end in constant time. And so we maintain both a head and a tail of the linked list. And that means we also have to maintain both a next and a previous in the nodes in that. But then all these add first, add last, remove first, and remove last all work in constant time. So I'll just make my frontier be a linked list then. So checking again to see here, this is called doubly linked list. Okay. So I'll say frontier is equal to doubly linked list. And then I'll say frontier.add first that vertex. Okay, so the frontier starts off with this vertex. And now I have a decision to make based on whether I'm doing breadth first search or depth first search. So if I'm doing breadth first search, then I will actually remove. I'll say v is equal to frontier.remove. Let me just check. I think I said it was called remove first. Yeah. So if I'm doing breadth first search, I want to take from the beginning of the frontier. Otherwise, I want to take from the end, which is like a pop on a list. But okay, so let's first make sure that if I were going to do depth first search using this data structure, so I haven't changed much. I've just replaced the list that was used to store the frontier with a doubly linked list. And so let me see now if I go along and I say I want to explore starting at 1, but I want to do a depth first search. So I'll see BFS is equal to false. Well, let's see, I get a little problem here. I meant to say doubly linked list, I think. And I still have a problem. Oh, I'm still tempted to say append. I want to add last. Okay, there we go. So I'm always adding to the end of the frontier. And the only choice I have to make is whether I'm going to remove from the front or remove from the end. Okay, so yeah, I guess I was just showing one of the directions here in the toString for this. But yeah, it comes out in the same order, 1, 0, 3, 7, 2, 5, 6, 4. I have to look back at the graph. Or is that the same order? Let me see. If I back up here, so I did 1. I guess it put the neighbors on in a slightly, okay, yeah, it actually won in a slightly different order, but it was still depth first here. So you notice we're always taking from the end here. So the order that you put the neighbors on the frontier is arbitrary, but you just want to make sure that they weren't there already. So yeah, in this case, it ends up going, so 0 comes out first. And actually 0 has no neighbors that were untouched. Then 3 comes out. 3's neighbors are 4, 1, and 7. 7's the only one that's been untouched. So I'll set 7 on fire. So now 7 comes out and burns to the ground. None of its neighbors are untouched. Then 2 comes out and we do that path there, 2, 5, 6. And then we end with 4. Okay, so the neighbors came out in a slightly different order, but the effect is the same. We completely finish exploring one direction before we back up and explore another one. Let's see what happens when we do breadth first search instead. So if I back up here, I start off at the beginning. And this time, okay, I happen to add the neighbors in this order, 3, 0, 2, 4. So 3 comes off first. Then 0 comes off, then 2 comes off, then 4 comes off. So interesting, in this case, I added these first. And 3 comes off first. And yeah, we set 7 on fire and 7 gets added to the queue. But we actually finish with, let's see, 2 is next. We finish with 2. You know, we set its neighbor on fire, but we finish with 2 first. And then we finish with 4. I think I missed 0. I meant to say we finish with 0 first, then we finish with 2. And then we finish with 4. So notice it finishes going out in this ring of fire first, before it finally then visits 7. So the first ring of radius 1 here, of a hop length 1 from where we start. And then now we're going to do the hop length 2, so that's 7 and 5. So we finish visit everything at hop length 1 first. That would be 0, 3, 2, and 4. So 1, 3. Let's see. Yeah, well 1 comes off, so 3, 0, 2, and 4. So hop length of 0, that's where we start. Then hop length of 1, 3, 0, 2, 4. Then hop length of 2, 7, and 5. Then hop length of 3, which is 6. That's the last one to come out here. Good, so it looks like we're working with breadth first search and depth first search. What I'd like to do now, though, is think carefully about the time complexity of this algorithm. So let's first of all realize that because I never add, I'm very careful not to ever add a vertex to the frontier more than once, right? So if it's already on the frontier, if it's already been visited, I do not add it again. So we can say that each node or each vertex passes through the frontier exactly once. So therefore, this loop is going to go through big O of V iterations. So we'll say, you know, given V vertices and E edges in the graph. So we notice that this loop goes through V iterations, or big O of V iterations. Now, because we're using a doubly linked list, removing the first or removing the last are both big O of 1 operations. So these are both constant time operations regardless of how many elements are on the frontier. So that's good. And then changing the status of one of these is also constant time. Okay, now I'm also going to assume here that because we're using a set data structure, we can iterate through the neighbors in time proportional to the number of neighbors. So this takes, you know, this goes through as many iterations as there are neighbors of V. And then this is also going to be a constant time operation here. So really what I have to figure out is, okay, how many times does this outer loop go through? And it does a bunch of constant time operations on each iteration. And then how many times does this inner loop go through total? And then it does a bunch of constant time operations. So one way to think about it, like we talked about in class, is, well, the most number of vertices that you could have as a neighbor is V. So we could say, okay, this inner loop goes through, you know, we could say big O of V iterations. So outer loop goes through V iterations, and then inner loop goes through V iterations, doing a bunch of constant time work, adding some constant time overhead. That's going to be big O of V squared. But we can actually come up with a slightly better bound than that. If we think about how many times does this loop iterate over all iterations of the outer loop. So if I were to have a counter in here, and I were to say counter plus equals 1, it's like, I'm going to read off what that counter says, and that counter is going to keep going over all iterations of the outer loop. And so what I realize is that we're in an undirected graph here. So if there is an edge in the graph, it means that so for example, this edge here, 2 is a neighbor of 1, but 1 is also a neighbor of 2. And so what we realize is each edge will contribute 2 iterations of this loop. So at first, when I'm looking at the edges coming out of 1, I look at 2, 3, 4, and 0. But then later, let's say I'm looking at 2. Well, I look at 5 and 1. And notice I already looked at the edge from 1 to 2. Now I'm going to look at the edge from 2 to 1. So it happens twice for each edge. So what I would say is the number of iterations here is actually big O of E iterations. So really it's 2E iterations. Or big O of E iterations for each, or overall iterations of the outer loop. So I say, okay, I have big O of E iterations in this loop doing a constant amount of work, and then I have big O of V iterations in this loop doing a constant amount of work. So the total time complexity, therefore, is big O of V plus E for both breadth first search and depth first search. And that's awesome. It just says, hey, we have to, we're going to have to look at all the vertices and all the edges in the graph, but not more than a constant number of times. Or we don't have to do more than a constant amount of work per each vertex or each edge. So this is a very efficient algorithm if we use the right data structure to represent the frontier, and if we use the right data structure to represent nodes having been visited or on the frontier or untouched. So that's why I decided to encapsulate this state within a vertex object, so I could in constant time update what the status was. Okay, so outer loop here goes to big O of V iterations. Inner loop here goes through 2E iterations overall of the iterations of the outer loop. So it's a constant amount of time times V plus constant amount of work times E. So big O of V plus E. That is a great algorithm. All right, so that's it for the moment for breadth first search, depth first search. These are extremely useful algorithms that come up all the time. Let me now, in the next video, I'll show you an application of this.